Okay, we had a lot of interesting discussions in the break, which you noticed. And there was a question about the Tij, the Maxwell stress tensor, why it was symmetric, how you could prove it. And then we suddenly realized it was very easy, because if I change E and J, and I and J everywhere, well, the formula looks the same, because this is just 1, 1, 1, 0, 0, 0, 0, 0, 0, 0. So flipping around the diagonal just moves around the zeros, doesn't change anything. And of course, multiplication commutes. So EI, EJ is EJ, EI. So as you can see, the Maxwell stress tensor is indeed symmetric. And it's very easy to see when you think a bit more cleverly. All right. And then back to where we were. Let's see. We had the following expression for the force. So we have that the force is equal to the divergence of the stress tensor minus the time rate of change in the momentum density in the electromagnetic field. And now we're going to integrate this to see if we can get a bit more physical feeling for what these mean. So let's see if I have some sort of volume with a surface. This is a small patch of the surface. And this is a vector. I will get this when I integrate over the surface. I will get t dot the normal vector. And this is still a vector, right? Because it's a rank 2 tensor times a rank 1 tensor. It's a so-called contraction or inner product. And we get out a rank 1 tensor, which is a vector. Okay. And there's a force acting on each little particle in this volume. And there is a momentum density. So if I have just a tiny box here, say, there's a momentum density stored within, and it's a vector, so it has a direction, right? So there's a small momentum stored in each little cube of space inside our volume. And now to calculate the total force on this volume, I just integrate, and I get minus d dt let's see, and again I use the divergence theorem, so this is just a surface integral, that's why I need this, and I get t like this, okay? And now the F is the total force on all the charges in my volume. Like this. And now this is the rate of change of all the momentum stored inside the volume, right? Because this is the momentum density. When I integrate it, I get the total stored momentum. And this is the time rate of change. And what is this? This is the flow of momentum out. And again, we're reminded why we need a tensor, because you can have flow of any component of the moment through any direction, meaning that, well, the surface is a vector, right? So you can have a flow of a 3-component vector in any of 3 directions. That's 3 by 3. It's a rank 2 tensor. So this is the flow of momentum in or out of the volume, depending on the sign we end up with. Yep.
What do you mean by integrating over del V?
By the surface of the volume. Same notation as we used before. V is the volume, or the region I'm interested in, and dV is the surface of it. Yeah, exactly. Okay. So it's just the integration region. Good question. Okay. Flow of momentum. Yeah. Okay. let's see. Yeah, and as with the Poynting's theorem, we could, where we could get the continuity equation directly from Maxwell's equations, we can actually do this here as well. If you start out with the Faraday law, and then you multiply it on the left by E, or you take the cross product by E from the left-hand side on both sides of the equation, and you do the same with the Ampere's law. Except now you do the cross product with the H from the left, and this is hard work, so I'm not going to go through it, but it's possible to start out here and get to this. Of course, halfway through this you'll have to figure out a good point to introduce the Maxwell stress tensor. Otherwise you're just going to end up with a component form which is going to be big and hairy. So again, as with the energy and the charge, the momentum conservation is just baked right into the Maxwell equations. So if you sort of play around with the Maxwell equations, you're not violating momentum conservation if you're doing it correctly. And that's an important result. But now to prove that this continuity equation is equivalent to saying that momentum is conserved, I'm going to prove that. Okay, and how do we do that? We start out by Newton's second law. And it reads the following. The time derivative of the mechanical momentum is equal to the force. If you write this out, it's m dot dv dt, right? That's what we have in Newton's second law. And if I want to connect this to the momentum density, I can just write it as an integral. The total momentum is an integral over the density. So I use a small p for the density of the momentum and a big P with the serif for the total momentum. So if it's unclear which one is which, you should just ask, and we'll try to sort it out. And well, I have some volume which I'm looking at, which does not have to be any particular shape or whatever. Yeah, and the PM is total momentum of all the particles in V. Because I can't have forces acting on a volume as such. I need, well, there is some physical entity here, a material which I'm working on, of course. And that's going to be the object that feels the force. Okay, and then from this equation, I could write this as an integral over the force density as well. And then we could see that since I didn't specify the volume, well, the integrands have to be the same, meaning that the mechanical force density is equal to the time derivative of the momentum density. Like this. Okay. And now if I insert into the continuity equation, which was F plus dt g divergence of t. If I now insert this expression into here, I get the following. I gather the time derivatives into this bracket. So this is the mechanical momentum density, and this is the electromagnetic momentum density. And I don't use a p on that because there's too many p's already. And this is equal to the flow of momentum. And this is now the balance, right? We have, this is exactly on the form of the continuity equation for charge. Because now this is all of the momentum. So it plays the role of the charge density. Here it's the momentum density. And this is the flow of momentum. Okay? Now you see the physics a bit more, I hope. Any questions on that? Nothing? Right? Now if I integrate the equation star over a volume to see, let's see, yeah. I'm going to try to prove now the momentum conservation. And to do that, I'm going to integrate over all of space, in fact, to see if momentum is conserved. And I guess you can pretty much see the result already. But if I set that Vm and G is the total electromagnetic and mechanical momentum in a volume V, Pm like this. And if I again integrate the right-hand side and let the volume go to infinity, well, one thing at a time perhaps, I integrate the right-hand side. And again, it's a surface integral. If I use the divergence theorem, now if I let the volume go to infinity, then the field should go to 0. And also, the t should go to 0 because it depends on the fields. Meaning that this should be equal to 0 as, and when I write v goes to infinity, it's a bit vague, but let's say I have a big sphere and I just inflate it until it covers all of space. So the right-hand side should be equal to 0. And then I'm left with the left-hand side. So 0 is equal to d dt. If I move the derivative here outside the integral, which is here, then I get Pm plus G. And now if the time rate of change is 0, this means that the quantity in the brackets must be conserved. And hence we have momentum conservation. And that's that. And you have to notice, of course, that there's no law saying that mechanical momentum is conserved separately from the electromagnetic one. So if I, let's say I accelerate an electron by using an electrical field, then I'm, of course, changing electromagnetic momentum into mechanical. And I could do the other way around, like in a generator, for example. And again, I think you should compare this now to, if you go back here, now that we integrated, you have some sort of feeling for what's each term. This is the time rate of change of the momentum, and this is the flow of momentum. Then we can compare it directly to dt rho plus grad j, divergence of j, sorry. This is the continuity equation for charge, right? And now this is, this plays the role of the charge density, and this is the current density. Okay? And we get it on this nice form when we sort of sum up all the momentum's contributions here together. Okay, and again, I would like to point out that the rho here is a scalar. And we describe the flow of that scalar by using a vector. But P and G are vectors, so we describe the flow of those vectors by using a tensor. You need something a bit bigger to fit the flow, so to speak. And this is, of course, because any of these three components of the P vector can flow through in any direction. So the x component of the momentum can flow in the y direction. Any questions? Some of you look a bit suspicious. Come on, it's okay to ask. No? Okay, if you insist. And as an example, I'm going to show you how to calculate the force on a sphere using the Maxwell stress tensor. Okay. This could be, for example, if you have an example of this is actually so-called optical tweezers. If you have the focus of a laser, like this, you could actually suspend a sphere inside here. People have done experiments on that. You can sort of see that if you move it to the sides, you have to pay some energy to do that. So you can actually use it to lift stuff around, sort of nano stuff, tweezers. And of course, it's hopeless to use mechanical tweezers, but optical is fine. So, but now, let's say I know the electromagnetic fields from this, let's say a laser or whatever, and I want to calculate what's the force on that sphere. And then I will start off in the following fashion. So this is a metal sphere, which has an area A, and I have an E and H field. If you want to use at least time-varying fields, you're going to have both, right? And I have, let's say, I'm looking at a volume which is finite, at least for now, and it has an outer area A prime. Okay, so V is the volume between A and A prime. And since this is metallic, I'm going to set the fields inside to 0. I'm going to assume that they're 0, that the metallic sphere sort of reflects the fields perfectly. Okay, so in metal, I set E 0, and then H must be 0 as well. And we apply the balance and the continuity equation. Pm plus G is equal to the divergence of T. And now if I integrate this over the volume V, I will get just the time derivative of the momentum in the volume, Pm plus G. And that's equal to the area integral of this one. Let's see. And that should be equal to 0. Why should it be equal to 0? Right. Because the fields, if we were far away, we imagine that the field should be 0 again. And on this surface the fields are going to be 0 as well because of the requirements on the continuity. I guess, yeah. Let's see. Now the force on the sphere then must be controlled by this balance here. Let's see. Yeah. And that's just the opposite of the, well, if we have some mechanical momentum popping up, then it must be disappearing from the electromagnetic field. And as it turns out, that's, I can write it as a volume integral. Now inside the particle-free volume here, in the volume V there's no particles, so there's no mechanical momentum. Then we have from this equation that dTg is equal to the divergence of t. So because I have only a physical object right here, the only flow of momentum I can have is purely electromagnetic, right? And let's see. Then I can write the force as an integral over the divergence of t. And then again, I can use the divergence theorem. And dV now is both the inner and the outer surface. And then I can just, by calculating t, I integrate over the surface locally. And I get out the force. So I need to specify the fields before I can move on, but it's a tedious process because first you need to calculate the fields, and then you need to calculate the stress tensor, which is all these field components. It's a lot of work, especially for if you're working in Cartesian coordinates and you want working on a sphere, then this integral. So it's a lot of work to do it for real. But there are some simple examples in the book which explains the procedure quite well. So I suggest, if you're interested, that you have a look there. Because I don't think we have time to go through a full calculation like that from scratch. Yeah?
What's the surface of the volume exactly? Is it A?
Prime and A. Right? You have an inner surface, A, and an outer surface, A prime. So usually you might set this to infinity, and the t will drop off, and there will be no flow momentum at infinity.
But when you use the divergence theorem from the first line to the second line, don't you need to integrate over the surface A as well?
No, not really, because there's no momentum flowing. I mean, if I look at the momentum balance of the whole space, then the momentum inside this must be conserved, right?
Yeah.
Yeah, so I'm just looking at this chunk of space and saying, okay, what goes on inside the sphere? It can't eat momentum. That's the idea. Okay, any other questions? I think the example in the book is actually a half sphere. But there's actually people that use this for research, and both theory calculations like this, and also to do the experiment in the lab, and then they use the Maxwell stress tensor to calculate the forces. Yep.
I don't really get this term here, how when you integrate over A prime, be A.
So I put a prime here. Is that okay?
Okay, yeah.
Yeah, I'm integrating over the outer surface. Yeah, that's why I put this, so it's specified. Okay, anything else? No? Okay, then I wipe the board, and then we have a brief discussion on angular momentum. Okay, we don't have time to go through the details of angular momentum, but I think you should see how it works, so you have some idea about conservation of that as well, and that the electromagnetic field can indeed carry angular momentum. Okay, and from mechanics we recall the following, that angular momentum is the position vector crossed with impulse. So this is again in terms of the densities, the momentum density and the angular momentum density. And the total angular momentum equivalent to the momentum density, we just integrate it over the volume we're interested in. Let's say I have a rotating wheel, then what's the angular momentum? I integrate the density of the angular momentum. Okay? And so this is the macroscopic angular momentum that you'll see. And we have for the electromagnetic angular momentum, it's completely equivalent to the mechanical one. You take R cross the electromagnetic angular momentum density. Okay? And this now is incidentally 1 over c squared and the Poynting's vector. Okay? And I can further expand this if I'm interested to read R cross D cross B. So here we relate the electric displacement and the magnetic flux density to the angular momentum. Okay, so we see that the electromagnetic fields can indeed carry an angular momentum, and it's pretty obvious that it has to be like this. And we can also derive a continuity equation for the angular momentum, but as you saw from the momentum, it's quite a job. We used maybe 1 hour on that, so I'm not going to go through the details. But you can read the result in Jackson. If you're really interested, I guess you have it in the library if you don't want to buy it. But the result is that, oh, not surprising, you have the time derivative of the mechanical momentum density and I said momentum density, I meant angular momentum density. The sum of the mechanical and electromagnetic momentum densities, angular momentum densities, is equal to, no, plus the divergence of a tensor M is equal to 0. And then M is not the stress tensor, but it plays the same role. It's the flow of angular momentum in direction, let's say I, through a surface oriented along direction J. That's the component Mij. And yeah, the LEM is given by this. I guess we used the G in the previous lecture on the momentum. And the M now is equal to the stress tensor T cross R. And if you're wondering what does the cross product mean here, then you could take out the permutation symbol, except now you might need another index. So the idea is to look at a component of this and use the permutation symbol to get the cross product. Okay, and that was a bit faster than I thought, but is there any questions on angular momentum density or any of the other topics that we discussed today?
When you have this conservation equation, you have the divergence potential on the left-hand side, and previously you had it on the right-hand side. Is that just sign conventions, or is there?
Yeah, there was a question on the sign here. I'm not 100% sure, but there's a sign somewhere. In the other equations, we had an equal sign here, and not this one. But I think if you see that you have R cross G here, it might be likely that there's a sign flip by flipping the two of these.
You mentioned earlier that the heat, also the tensor, the stress tensor, sometimes was timed with well, with a -1.
Yeah.
This one. And if it's just timed that way, then everything is consistent with what we think.
Yeah. It could also be that you just change the order of the cross product, for example, or something. Okay, there's might be a sign error, of course. Also, as always, the signs are dangerous, but you get a continuity equation which is analogous to the one for momentum. Anything else? Okay, I'll see you on Monday then.